update on the MaNGA survey.
Talk. Hello. All right, better. Okay, so you have this wealth of information that comes from the spectra, and I think what Sloan has taught us is that if you can observe a large sample and place that information into a powerful statistical framework, you can begin to understand how the population of galaxies at redshift 0 came about, and from that information get important constraints on formation models. So you can map out the color magnitude diagram. You can look at higher order data products, age versus mass, and you can begin to see how these distributions are populated. The problem, of course, is that we're still dealing with galaxies as point sources. Of course, they're not point sources. They have this rich information, this rich structure that we're missing with our slit or our fiber just placed at the center. And so, of course, what we would really like to do is have spectroscopic information across the entire face of the galaxies in our sample, but be able to do this for a very large sample so that we can go back and enjoy the statistical constraints that Sloan and other large surveys have been able to provide. So this motivates IFU surveys, and I thought for this audience, it might be useful to just give a little cheat sheet about the sort of modern, large IFU surveys that are out there and available and may be of use for you for different reasons. So I just want to focus on three. The Khalifa survey is the first. It's actually finished now, about 670 galaxies. The spatial resolution is just under a kpc. The signal to noise per resolution element per spatial element at an effective radius is about 30. So this is a good place to go for the next step beyond Atlas 3D, better spatial resolution, somewhat higher signal to noise. If you're interested in larger data sets, more statistical power, then I recommend looking at SAMI and MaNGA. So here you can see the samples of galaxies that are coming available very soon. In the SAMI survey in July, it's about 1,600 galaxies that are going to be released. In December of this year, MaNGA, my survey, we're going to release 4,700 galaxies. And you can see SAMI and MaNGA are somewhat similar in terms of spatial resolution, more like 1 to 2 kiloparsecs median resolution. Signal to noise a little bit lower than what you can get from Khalifa. So these data sets are out there, they're increasing in size, and I encourage you to go and make use of them. So let me focus now on MaNGA. MaNGA stands for Mapping Nearby Galaxies at Apache Point Observatory, and our goal is to reach 10,000 galaxies by the end of our survey. So here's a little bit about the project and the instrumentation that let us achieve our goals. So this is part of the Sloan 4 program, which began in 2014. And our observations are on track to reach 10,000 galaxies by the time we finish in 2020. The way we're doing this is we're taking over 1,400 optical fibers from the BOSS spectrographs, the previous Sloan survey, and we've arranged these into bundles of different sizes, 17 IFUs per plate, which we then use to target the galaxies in our sample. And so this is how we're able to, over a couple of years, build these very large samples. Here is an example of the kinds of galaxies that we're looking at in any given plate. This is actually our first commissioning plate. And so you can see it's a mix of different galaxies with a range of projected sizes on the sky. little more information about the survey. Spatial resolution, as I said, is about 2 kiloparsecs. The spectral resolution corresponds to about 60 kilometers per second. A very large wavelength range, 3,600 angstroms out to a micron. And signal to noise, we observe until we reach a certain threshold that allows us to get good quality information even in the outskirts of our galaxies. So these are about 3 to 4 hours exposures. The sample is a series of volume-limited samples. It's complete down to about 10 to the 9 solar masses. It's selected in a way that delivers a flat distribution in log stellar mass and tries to flatten for effects in color. So when you go to the data and you want to use it, look for weights that allow you to correct back to a complete representative sample. But this allows us to improve statistics at the high mass end and in rare parts of color mass space. We're also able to achieve a fairly uniform radial coverage. 2/3 of the sample reaches 1.5 effective radii. 1/3 of the sample reaches 2.5 effective radii. And there's more information in a series of papers. These are 2 good ones to start with if you're interested. So currently we've observed something like 6,500 galaxies. Our next data release is in December. As I said, there'll be 4,700 galaxies made available. But this is a really big data release for us because it's more than just increasing the sample size. We're releasing some new data products. So I just want to highlight that for a second. We're going to be delivering the measurement maps that we have been using inside the collaboration. So these are maps of stellar and gas kinematics, emission line information, stellar absorption indices, and other quantities that we've derived from the data cubes. So those will be made available. In addition, we're going to release a website and a tool package that we call Marvin that is designed to give you a very seamless, interactive way of working with the data. So there'll be a website that you'll be able to go to your favorite galaxy, click on a location within that galaxy and see the spectrum corresponding to that location, as well as get information about the higher level data products. But more importantly, you'll be able to download a set of Python tools that will let you work with the data regardless if it's on your laptop or remotely. We're trying to make it very seamless and easy to interact with. So look out for that. Finally, MaNGA is also conducting a stellar library during the bright time. We're observing thousands of stars. So this will be the largest stellar library. We're going to have our first release of those data products in December as well, about 5,000 stars, covering our full wavelength range and hopefully filling in parameter space in terms of the stellar models, the stellar templates that go into galaxy models that we use all the time. Okay, so I want to spend the rest of the talk highlighting a couple of results. I've put some of my favorite results up here on this slide, and of course it's very difficult for me to try to convey everything that's going on, which is a good place to be in. But I wanted to focus on 3 different topics and highlight 3 different results that I think are particularly exciting for this audience. So staying with the theme that Aaron started with, early type assembly, I want to talk about this paper by Mark Graham and Michele Capillari. It's sort of our view of the angular momentum question that Aaron nicely introduced. Also mentioned Greco's work that he showed earlier this morning about the building up of the outskirts of early type galaxies. I'll talk about fueling star formation, and I want to specifically mention Francesco Belfiore's work on radial profiles of star formation in the Green Valley. Francesco will be talking tomorrow about a different topic, so I'll say a few words about that one. And finally, quenched galaxies. I want to focus on what we call red geysers and how they may be playing a role suppressing star formation at late times in quenched galaxies. Okay, so let's get started. This is the same topic that Aaron was just talking about, dynamical assembly histories and what the angular momentum distribution and dynamics of early types is telling us about their assembly history. So this is a plot that Aaron actually introduced. We're looking at this lambda parameter, a proxy for relative angular momentum against projected ellipticity. And this is the result from Atlas 3D that we had for a while. Let's ignore the color coding for the time being. Aaron mentioned that this is typically divided into fast and slow rotators. But there has been some debate about whether this is a continuum distribution or whether there's actually a dichotomy between these two populations. Here is the result from SAMI, and Aaron showed some nice work suggesting that there was indeed a dichotomy and that we should think of these as two different populations. That is certainly consistent with what Mark Graham and collaborators are finding in the MaNGA data. So here is the MaNGA sample as of a year or so ago on this particular plot. And what we see is indeed there's this overdensity down here in the slow rotator category. So we really think that this is a distinct population. I just want to mention, this is something that Aaron hinted at as well. Here, the color coding is by visual morphology. And you notice that there's quite a bit of spread and overlap across this diagram. If you use kinematic morphology, the shape of the velocity field, you find a much cleaner separation in different types of galaxies across this sequence. So this is connecting angular momentum with the kinematics, with the actual order in the velocity field in an interesting way. And let me also point out another result from the MaNGA data by Becky Smethurst that compares at fixed mass the star formation assembly history, the star formation history, I should say, of galaxies' slow rotators versus fast rotators, and finds that the formation history is actually different. So fast rotators have star formation histories that seem to quench at later times compared to slow rotators. So again, we're adding evidence to this picture that Aaron talked about. These are really distinct populations, and it's interesting to think about what caused these two different populations to arise at the present day. I want to mention in this context Greco's talk from earlier today, because I think it's relevant and quite exciting. So here, Greco is showing metallicity profiles in different mass bins from the MaNGA data from stacks. And again, he's finding that these are not well fit by linear relations, and we're seeing this flattening that's occurring at increasingly smaller radii as you go to higher mass galaxies. So this is at least consistent with the idea that perhaps the metallicity in the outskirts here is affected by the assembly of satellites building the outskirts of early type galaxies. Let me move to this topic and this question: do galaxies quench from the inside out? And I like this topic because it was one of the early questions that we wrote down for MaNGA, and I think Francesco Belfiore has done a really nice job of addressing it. And of course, the reason to ask a question like this is because so many models of quenching invoke a central AGN, a feedback process that might turn off star formation. You might think that that would then occur from the center, and the quenching then would then work its way out to the outskirts over time. So we're taking a first look at this scenario, and what Francesco has done is studied the transition through the Green Valley, and you might think, based on previous work, that you could explain Green Valley galaxies as simply having a central bulge with little or no star formation, combined with star formation in the outskirts. And so that would give you the green colors, and then as that galaxy moves closer, moves onto the red sequence, that region of quenched galaxy is expanding to larger and larger radii. And so that's certainly consistent with work that looks at the surface mass density of these different populations. And so Francesco went out and tested it. And here what he's showing is profiles in specific star formation rate. So specific star formation rate is a function of radius for different mass bins. This is the least massive galaxies up to the, least massive to the most massive galaxies. And these are all from the star-forming region of the main sequence diagram, if you like. And then over here, the same thing, but looking at just Green Valley galaxies. Okay, so what we see here is that, yes, indeed, there is suppression of star formation in the centers of Green Valley galaxies, as you might expect, but there's also suppression occurring in the outskirts as well. So it's not just in the center moving out. We're seeing effects in the outer regions of Green Valley galaxies. I was interested to see Sandro's talk earlier today. I'm wondering if things are maybe different at Redshift 2. Perhaps that's something that we should look at a little more carefully. And then I just want to point out another work from MaNGA. This is by Ashley Spindler, seeing very much the same thing. So here we have star-forming galaxies. These are centrally suppressed galaxies, not exactly Green Valley, but similar, and you see that indeed they don't reach the same level of specific star formation rate in the outskirts as the star-forming population. This plot is also interesting because it compares centrals and satellites. The centrals are dashed curves, the satellites are solid curves. And so this work is important because it actually finds differences in the profiles, the star formation rate profiles of centrals and satellites, not just in relative fractions, but in the actual distribution of star formation in galaxies that are identified as centrals or satellites. Okay, let me come to my last topic, my last question. How do galaxies stay dead? This is something I've been particularly interested in ever since we looked at images like this. We were curious to understand if MaNGA could tell us something about otherwise red and dead galaxies. So we looked at samples like this, where the images just show sort of typical early type galaxies. But we noticed that when we plotted images of equivalent widths of strong emission lines in the MaNGA data, we saw these interesting features occasionally that would pop up. And fairly weak, but sort of bisymmetric, connected to the nucleus of these galaxies. And we thought, what is going on? To us, they looked like flows of material coming out from the center. Since they were in red galaxies, we decided to call them red geysers. And it's been very interesting to study these systems and try to find out whether they're actually telling us something interesting about late stages of galaxy evolution. So in 2016, Edmund Chung and I and others wrote this paper about our prototypical example, a red geyser here with a star-forming companion. And we tried to very carefully demonstrate that, at least in this particular object, it seems like there's evidence that this red geyser feature is associated with a wind, and that wind could plausibly be connected to suppressed star formation in this particular galaxy. So we would expect there to be star formation. There's cold gas in this system. There's no star formation detected, and yet there's ionized gas everywhere, which is not consistent with rotation. It seems to be coming out of the galaxy. Some of it is moving at speeds beyond the escape velocity. The galaxy has a radio AGN with energy that's sufficient to drive this wind, and the energy in the wind exceeds the cooling rate of the gas. So it's an interesting story that suggests that maybe in this system there's something interesting happening with respect to this wind and the suppression of star formation. But what I think is particularly exciting about this population is that it's relatively common. So on the red sequence, we're seeing these features in 5 to 10% of quenched galaxies. And if you think of it as an episodic phenomenon, this suggests that this red geyser phase is happening every couple 100 million years, which is not dissimilar to merger times for minor mergers or catastrophic infall events. So it may indeed be a maintenance mode kind of feedback mechanism that could help suppress star formation at late times. I want to highlight a talk by Namrata Roy that I think is coming on Thursday. So one of the predictions of this interpretation is that the red geysers ought to have AGN activity, because we think it's low luminosity AGN that's responsible for driving this wind. Unfortunately, the AGN signal is fairly weak, and radio galaxy surveys are not deep enough to detect many of these systems individually. So what Namrata has done is stacked red geyser radio signals and compared that to stacks of a control sample. And what she finds is that galaxies with red geyser signatures in the optical MaNGA data show enhanced stacked radio flux compared to control samples that are otherwise identical. And so we think this is intriguing evidence that suggests there is a correlation between these red geyser features and enhanced radio AGN activity. And that leads to supporting evidence for this picture of AGN-driven winds in these systems. Okay, let me wrap up. So MaNGA is about halfway done. We're mapping 10,000 nearby galaxies. We have this big data release that's coming in December, more galaxies, and some new data products that will hopefully be of interest. I talked about some work that we were doing on early type galaxies. It looks like slow rotators are indeed a distinct class, as Aaron also described, likely with a unique assembly history that may be something worth thinking a little more about. We're also finding evidence for enriched outskirts that seems consistent, at least, with satellite accretion. I talked about quenching. We're finding evidence that quenching is happening at all radii, not just in the center, at least among galaxies that are in transition or appear to be transitioning from the star-forming cloud onto the red sequence. And finally, I mentioned these surprisingly common red geysers, which may be related to suppression of star formation at late times, and we now know are associated with enhanced rates of AGN activity. So I will stop there. Thank you.
Joel. Sure.
So one of the topics you discussed was this special population, which I think we first learned about from Atlas 3D, of galaxies that are in the rotation versus shape plane, round or pretty round, and essentially non-rotating. And the question is, how do these things form? Now, in merger simulations, especially cosmological ones, galaxies tend to form on filaments in the cosmic web, and the simulations usually have mergers occurring basically along the filament. And when you have an axis like that, it's essentially impossible to make round, non-rotating galaxies because the mergers are always going to bring in angular momentum, and it'll tend to be in the same direction, more or less. In simulations, the way that we could make these round galaxies was basically in a node where you have cosmic web crossing, and you have material coming in from several different directions. So, question, is there also something peculiar in the environment of those galaxies? Do they particularly occur in nodes in the cosmic web, i.e. These densest regions?
I think there's some debate in the literature about this. So Jenny Green has actually used MaNGA data to try to address this question. I don't know, is Alexi in the audience? She didn't come to my talk. I should have guessed. So Alexi and Jenny looked at the environmental signatures, and I think the jury is still out. There was a claim that there was a greater association with ECGs and central objects, but that has flipped, and there was also a claim that they were slow rotators were more common in the cores of massive clusters or massive halos, but now I know that people have been finding them at larger radii. So I don't think I can answer it. It's something that people are looking into, but I don't know if it's clear yet.
It's a good question. Horizon APN, Eagle. Nation has problems of different origins. I've seen that they've discussed, but maybe you guys have already discussed the origin of non-rotating century bound galaxies.
No. What does that mean? Interesting. You need a certain amount of halo mass to have your X-ray halo or what have you, to have that reservoir there. Yeah. Yeah, interesting. Something to think about.
Yeah, so I was actually very surprised about the AGN red geyser correlation because of this idea that the AGN feedback events might be very short temporally. So when you see the outflow and when the AGN generates the outflow, probably are at different times. You might actually not expect it. I was wondering if you could comment on that. Also, maybe whole gas follow-ups, molecular submolecular follow-ups.
Yeah.
Geysers to see if it's whole gas now.
Right. So on the first question, is Namrata in the audience? Oh, she's right next to you. Okay. So Namrata should answer this question, but you can look at detected radio AGN that MaNGA could have seen, or is in the MaNGA sample, or is it at least in SDSS, and are not geysers. And there's some large fraction of radio AGN that don't have geyser signatures. So it's still possible, I think, that you could have a mismatch or an out of phase, light curves between the geyser phenomenon and the radio AGN. But maybe, do you want to say any more about that? Do you remember the numbers?
Yeah, so there is for the galaxies with ionized gas, but they are not quite so the AGN geyser signatures. Yeah, so they do a fraction of those do have like a radio AGN like signatures, but they do not show like the geyser signatures. So we say that maybe this is like a time problem. So they might show geyser activity at some point in the future, but they do not show it right now.
Remember, 10% or 90%?
It's like 10, 15, definitely not.
And she'll also talk about another category of interesting.
Yeah, we did like a back of the envelope like an energetic calculation, so we kind of like took the radio power and we see that how much kinetic energy that can have like from the one-time relation between the kinetic energy and radio power, and we see that it kind of has the power to calculate the creation from the yeah.
There was a second question in there.
Kind of like almost follow-up or something.
Oh, yeah. One thing that we want to do is look at more local samples. So Khalifa, as I mentioned, and Atlas 3D, we think that there are some examples of these objects in those samples. So the next thing to do would be to look at data that we already have, see what it tells us.
Okay, let's thank him again.